Good morning, everyone. Well, I guess we're back into our springtime weather, but it might be a little bit cooler some days during the week. But still, I guess we're definitely spring now. I hope everyone's doing well this morning. Uh, the calendar, as far as our class is concerned, shows that we will have our next test during the next week. So by the end of the week, I will make another announcement about that. Of course, it'll be the same window of time that we always have, the Thursday to the Friday, just to keep everything stable. I think maybe one thing in your life is that you've got your pre-cal test at the same time. And so that's one less thing maybe to have to worry about. And so I'll have more specific things to say about that in the email announcement, but it's the same routine, the turning in your work as you normally do. So nothing any different. Um, what I want to do today is to continue with the ideas that we started last lecture. That is, we moved to the unit circle and started looking at the abstract concept of angle, which is actually more common to you than the distance along the unit circle. And so now what we want to do is to look at the imposed right triangles that we have on the unit circle and approach trigonometry through those triangles. Now, what's nice about that is that the triangles will give you more flexibility with different kinds of problems, but the computations will be the same. In chapter 5, we had reference number. In chapter 6, we have reference angle. It's the same thing. There's no difference in the computation. Doing algebraic expressions, no change. The only thing that we have now, for instance, if you compute values of trig functions, no change. What we're going to do is introduce the right triangle and give you a new approach that again will make problems obviously with triangles simpler, but will also make what you have as far as your toolbox and approaches that you have more flexible. So I think when we started this, you probably were thinking in the back of your mind, wow, when are we going to get to those right triangles? Professor Ron uses the Pythagorean theorem every other problem that he does. Well, the unit circle and the right triangles are actually the same. And so now, like I said before, we did the unit circle to introduce the concepts of inverse trig functions. And now with the triangles, we'll have even more flexibility. And I think you'll enjoy the way the two interpretations or approaches mesh together. When you take your calculus, you'll certainly see aspects of either as you work problems. So remember, remember, when you define a discipline in mathematics, it can be derived through very different approaches. The approaches that we're using now for trigonometry are based on geometry. Okay. Now, when you get to calculus and you work into Cal 1 and Cal 2, you're going to see an approach that's more real analytic, but you're still not going to forget what we've done in pre-cal because these approaches will be extremely important. So just remember, in math, we just keep building the tier. We do the same thing over and over, but we add new stuff to increase our knowledge. So just remember, increasing knowledge is not a bad thing. It makes us more astute at what we do. So let me go ahead and share my screen. Now, what I was saying before has to do with what I've written here on this sheet. So we're going to find that 6.2 and 6.3 are kind of meshed together. And then, of course, 6.4, we'll be doing the same type of calculation with the inverse trig functions, but now we're going to add the right triangle that will allow us to do different compositions. For instance, we know a lot about the inverse equations because we had to figure out the range and domains of the inverse trig functions and then show when they were valid. So that's practice we've already done. But there's one other aspect that we can do that we could have introduced in chapter 5, but I usually wait to the right triangles to make it a little bit easier to transition into a different type of composition. So we'll see that too. So when it comes to the unit circle, what I've done here, I've drawn S1. And so when we think of the unit circle, we have a distance from the point 1, 0 to the terminal point. So that's how we measure distance on the unit circle. And last week, we made the connection or correspondence between the angle theta and the distance t. And so we're thinking, okay, that's good. So it doesn't matter if we use t or theta as long as we're working with the unit circle. But what we're going to find is that as we extend to other larger circles, we see the relationship between t and theta actually changes. That is, the arc length will be r times theta. So what we're thinking of, or theta times r, however you want to say it. And so when we look at that, we're thinking, okay, well, as the radius of the circle changes, the relationship changes here. Of course, when r is equal to 1, they're the same. And so that's what we termed arc length. And then, of course, we got the angular velocity and the linear velocity. We talked about degree measure, because let's face it, we love degrees. So what we want to do now is think of a way that we can associate the theta with different circles, but not have to worry about changing anything, in the sense that theta will work for any size circle. And how do we do it? We use the triangles. So first, what I want to see here is that for this particular terminal point, we have an imposed right triangle. We can think of the distance x here from 0 of the origin to this point as a leg of a right triangle. And then, of course, the y coordinate here as another distance from the x-axis to the point xy as a leg for a right triangle. And so now we're thinking, okay, right triangles have non-negative parts, in the sense that we don't really think of triangles as having directed lengths. They're not negative. So the idea of reference triangle will basically harken back to reference number, where we look in the first quadrant, where the cosine and the sine, that is the x and the y, are positive. And so now what we can see here is that this is basically the equation of the unit circle. X squared plus y squared equals 1. So we're fine with that. Now, what we want to do is say, okay, what if we have a larger triangle? For instance, if we just focus here on the unit circle, we can say, well, again, this distance here is x. This distance here is y. And in terms of the right triangle, we can think of a ratio. That is, for instance, from S1, we can define the following. Number one, cosine of theta, now we're going to focus on theta instead of t, can just be x divided by 1. Looking at the ratios of sides of the right triangle. And then, of course, 2, sine of theta can just be y over 1. And you're thinking, well, why are we doing that? Why are we dividing by the length of the hypotenuse? I mean, it's just 1. What good is that doing? Well, it's setting up an algorithm that's going to allow us to inject similar triangles. Now, if we look at this and we think of the angle and the sides relative to that angle, we can think of x as being adjacent to angle theta, adjacent. And so what we would do, instead of write adjacent, because we're lazy, we would write ADG for adjacent. And then, of course, 1 represents the hypotenuse. So we say hypotenuse, HYP. Now, another thing that we're going to notice when we extend to this triangle, we can also use letters that we like. So I'll mention that shortly. Now, for the sign, let's do the same thing. If we're thinking about the triangle, it makes sense to, again, think about ratios of corresponding sides. So for instance, here we see the opposite side to theta, opposite side just has length y. Again, that will be OPP. And again, when we talk about the side of the triangle, we're talking about where it's positioned in its length. So it's kind of a twofer. You know, in geometry, we're really lazy, but we like it. And then, of course, dividing by 1, we have the hypotenuse. Now, what would make any of this make sense? Why would we even be interested in this? Well, we have the theorem called the law of similar triangles. Now, what I've constructed here is another right triangle that is equiangular to this smaller triangle. That is, it's similar. So we can say the following. The trig functions can be defined unambiguously. That's a fancy word. That just means that it will be clear, can be defined unambiguously using the law of similar triangles. And this theorem is not easy to prove. The law of similar triangles. I did it one time in an honors section, and they said, "Professor Ron, this is hard." I said, "Yeah, it was. It was difficult, but you should research that. It's a beautiful result. We depend on it." Okay, so the trig functions can be defined unambiguously using the law of similar triangles. So that means that how we use the unit circle to find the trig functions is completely consistent. If we extend to right triangles, then how can we do it so it's equivalent to what we have in the unit circle? That is, these, whatever we have here, this should be the same for the bigger triangle or even a triangle smaller than this. Otherwise, this would just be completely incorrect. So now what we can see is the sides or corresponding sides of similar triangles are in ratio equal. So now what we can do is the following. We'll look at the larger triangle and notice what I've used here. I've used a script X and a script Y and an uppercase R for the radius. So now we can look at the same thing and say that the X to 1 will also be equal to the script X to the script R by the law of similar triangles. So we have this. And again, I'll just point here, law of similar triangles. We're going to use it in both of these cases. And likewise here, by the law of similar triangles, we should be able to take the opposite to the hypotenuse, that is y to r. And this will work for any triangle, right triangle, that is similar to the triangle in the unit circle. Even a smaller triangle, that is one that's in the triangle that's smaller than this one, or any larger triangle. And I'll just say this works for any similar right triangle. So when we think of similar angles or similar triangles, we're thinking of triangles that are equiangular. That is, we have corresponding angles that are congruent. And the beauty is that this is such a common use in geometry and analysis. It reminds us of the Pythagorean theorem. We think, oh my goodness, what would we do without those two results? We really would have to work a lot harder. So now we're thinking, okay, well, if we've done all of this for cosine and sine, now we can just take the definitions of the remaining four and write new uh, definitions for them using the right triangle. Now, what I've done here, I've used the script X and the script R, which is fine. Normally, we'll just use like a lowercase x and a lowercase r, but I didn't want to diverge from the notation that I had been using all along. So now what we can do, and again, we'll relax this notation when we do examples, just because again, we're lazy. So what does that mean for the rest of them? So we can now do tangent theta, by definition, is sine theta over cosine theta. And of course, now the theta can run through all positive reals and all negative reals, just like t. So theta replaces t and gives us the domain and range, or the domain that we're accustomed to from the unit circle. And then, of course, for the remaining trig functions, we have the same domain and range because nothing's changed. So I like it when students say, wow, this is easy, Professor Ron. We've already worked so hard in chapter 5, and now we can ride the wave. And the triangles you like better anyway because you've had more experience with them. So now this will be y divided by r divided by x divided by r. And of course, the r's absorb, and we get y over x. Now, if we want to, be kind of pedestrian, we say, well, that's just what opposite over adjacent. So formally, we can define the tangent of theta this way as y over x, but then we can use the actual positioning of the right triangle sides and write it as opposite over adjacent, which is very helpful geometrically, like adjacent over hypotenuse for cosine and opposite over hypotenuse for sine. And now we can be lazy. We don't have to work hard for cotangent. Cotangent is just the reciprocal of tangent. So now we can just flip this around without having to go through all of this. So this, by analogy, will be x over y. Again, just thinking about the right triangle here, the larger one, and this will just be adjacent over opposite. Now you're thinking probably what trig functions will get the most use? Probably the cosine and the sine and the tangent, but it doesn't mean that the others aren't good. It's just that we'll probably end up using them more because they're more theorems stated in terms of those particular trig functions. Now, lastly, we've got two more. Secant theta is 1 over cosine by definition. So we'll just be a little bit more formal with this. So if we take the reciprocal of the cosine, this will just be r over x, and we get the same domains as we had before. But you see how much better the unit circle is for functions. It's truly, triangles are nice, but the unit circle is where we have to start if we want to put everything on the most even playing field. And so now this will be hypotenuse over adjacent. And lastly, we have cosecant. Cosecant of theta will now be the reciprocal of the sine, 1 over sine. I mean, if this were any easier, we would say it's just false. So 1 over sine will give us r over y. So you don't really have to memorize all of these, just know the sine and cosine, and then you can get everything else using your definitions from chapter 5. And so this will be hypotenuse over opposite. So the reason that we can have such a convenient reinterpretation of trigonometry is because of the law of similar triangles. Well, it all really started with the Pythagorean theorem in the unit circle, but the law of similar triangles allows us to take our interpretation from the unit circle and transfer it to right triangles. So again, we have all these linch pins. A linch pin, used to be where back in the olden days, it was the pin that kept the tire on the axle. If you have a wheelbarrow, it keeps the wheel on the axle. And if the linch pin comes out, then you're in trouble. The wheel's going to eventually fall off. So we think of these major results as just being the glue that holds everything together. Without it, we couldn't do what we just did here. And it's so simple. Like I said before, we love triangles because we have so much use for them, and we have so much experience with them. I mean, when you think about all your colleagues that are in certifications like electricians, plumbers, surveyors, they use trigonometry almost with every appointment or task that they have to do. And the trigonometry is essential. I mean, for surveyors, you live for it, and they have their equipment. You can see them doing their measurements when new buildings and new constructions go up. Their work is essential. And so I used to think at one time that if a STEM major needed a nice summertime job or something, work with some surveying company and learn some neat things about how that science works and get paid for it, or just work for free. But working for free is kind of tough during these times. But again, that is trigonometry is very essential, and they find it useful to use this new interpretation. Okay, so now what we want to do is, now since we're talking about some triangles, just solve some problems with some right triangles, or basically where we have a figure that's decomposed into right triangles, we can use these new definitions to solve it. So like I say, everything is the same now. We just have the right triangles with these new definitions just to add to what we already know how to do. Now, I want to first focus on two very famous triangles. So we'll just say famous right triangles. Sometimes we don't want to have to work so hard, so we want to focus on some constructs that are simple. But we can always use those ratios of the sides of the right triangle to get us out of a tough position if we, lose our minds, or so to speak. So the first thing we're going to do is think of the 45, 45, 90. So if you look at a square, and I'll just say the square has an edge length of L. So now we're back into our geometry class. Euclidean geometry is an elegant study and gets complicated really fast, just like number theory. So now what we want to do is draw a diagonal to basically bisect the angles. Again, you prove that in geometry. So we have a L, a square. And now, of course, when we bisect, and what's nice about the right triangle is that the two acute triangles, or two acute right angles, I'll get it eventually, the two acute angles are complementary. That is, their angle sum is pi over 2 radians, or 90 degrees. So that's like, wow, how nice is that? So of course, if these are congruent, we would have a 45 degree. So we'll be lazy and use our 45 degree, our degree measure. And when we look at this, we're thinking, okay, well, this is a nice triangle. It's isosceles. So now what does this imply? Well, for our 45, 45, 90 triangle, we'll just have L squared. And of course here, if you like, we'll just call this H for hypotenuse, just to give it a letter. So we have L squared plus L squared equals H squared. So 2L squared equals H squared. So now, again, we're thinking, when we look at this, we're thinking square root property. But again, we're only interested in the non-negative agreement here. So L squared will be h squared over 2. And then by square root property, we have L equals plus or minus the square root of h squared over 2. But of course, this is plus or minus the square root of h squared, which is the absolute value of h over 2. But of course, here the absolute value of h is just h because we have a length non-negative. So this is plus or minus h. Now, when you look at this, we've got the square root of 2 downstairs. Let me not forget the radical there. And then we select plus. So this says that L is just h divided by the square root of 2. So when we're looking at a 45, 45, 90, you're thinking, well, this is just in concert with the terminal point on the unit circle, 1 over root 2, 1 over root 2. So same thing. Well, not a surprise. Of course, it's not a surprise. You already knew this. So now we're thinking if we have the hypotenuse, we can find the leg by dividing that by the root of 2. Or if we have the leg, we can find the hypotenuse by multiplying the leg by the root of 2. So maybe this is easy. Again, you could use your trig functions with this, but this is a very famous triangle that comes up all the time. And you know, it's easy, so let's use it. Now, the second one, we want to start with an equilateral triangle and get the 30, 60, 90. So I'll just write over here 45, 45, 90. So now let's start with isosceles. We're not actually, we're going to make isosceles, but we're going to start with equilateral. You can say equilateral or equilateral. Probably more professors say equilateral, like, you know, but you think equator or equator, equilateral, you choose. So now when you look at this with the equilateral triangle, we have equiangular angles. That is, they're all 60 degrees. So we have 60 degrees here, 60 degrees. And then we want to bisect, that is the angle and the opposite side. We can do this via construction. So now when we look at this particular setup, if we bisect this angle, we get a 30-degree angle here by construction. And then the perpendicular bisector not only gives us a 30-degree angle here, but it basically takes this side and cuts it in half. So if you like, we can just call this side H. And now we'll call this shorter side S, but we know what it's going to be. It's going to be H over 2. We get that for free, but let's just write it for now. And then because we're lazy, we'll use L for longer side. So with the 30, 60, 90, 30, 60, 90, we have this setup where H will be hypotenuse, L is longer side, and S will just be the shorter side. Again, the shorter side opposite the smaller angle, the longer side opposite the larger angle. Again, geometry is very user-friendly lots of times. So now, again, we can look at this and say, well, we already see by the perpendicular bisector that S equals H over 2. We get that for free. So that's easy. And then, of course, by the Pythagorean theorem, we can just say H squared over 4 plus, again, S squared is H squared over 4 plus L squared equals H squared by the Pythagorean theorem. Again, S squared plus L squared equals H squared. But then, of course, we just just like up here. So equivalently, L squared will have, again, we'll take 1/4 of h squared from h squared to give us 3/4 h squared. Now by the square root property, we have L equals the square root of 3/4 h squared. So the same song and dance, which will give us the square root, oh, and of course, plus or minus. Let me not be bad about that. We'll have to select. So we have plus or minus square root 3. Of course, the square root of 4 is 2. And we have the square root of h squared. This gives us plus or minus square root 3 over 2 times the absolute value of h, which by definition here would just be h. So we have plus or minus square root 3 over 2h. And now, of course, we select positive, non-negative quantities. So now we have L equals the square root of 3 over 2h. Again, no surprise. S is 1/2. We think terminal points, root 3 over 2, 1/2, and then 1/2 root 3 over 2. Again, not a surprise. This should be consistent. So now what we're seeing is that when we have a 30, 60, 90 triangle, if we have, in this case, if we have the H, we can always work through this. That is, if we have the S, we can figure out H, and then of course, we can figure out L. But notice here that when we look at the two, we're just seeing that S will be the square root of 3 times L. Also, as an extra, just comparing these two, S is just the square root of 3 times L. There's another way of looking at it if you just want to compare these two. So when we want to get S, we can take L and hit it with square root of 3, and we'll have an equivalent equation. So how you want to look at these things, students say, well, when I get to 30, 60, 90, Professor Ron, I'll just use the trig functions. But these triangles come up so much that it's actually very useful to be familiar with them. Put these on note cards. And I'm sure when you took high school geometry, you spent some time on this. And you probably even did some trig with right triangles. So now you're thinking, breathing a sigh of relief that you're seeing something that seems somewhat familiar. Okay, so there are our new famous triangles, or new or old famous triangles. So what I want to do are just a couple of examples where we use our newfound friends, our right triangles, to actually solve some problems. So here's the first one. And in this case, we are asked to compute X. So now, again, it does really feel like we're in a physics class. So in this case, we have a triangles within a triangle. Some really, really interesting WebAssign problems that'll make you feel like you're in high school geometry again. So here's the figure that we have. So for this particular figure, we have the following as given. We, of course, have a right triangle here. Again, if we're going to use trigonometry, we've got to have a right triangle somewhere. We have a distance of 100 here for this particular leg. We have 60 degrees here, and we have 30 degrees here. Now, what we want to do, and you're thinking compute X, well, where's X? X is denoted right here. So now when you look at this particular problem, you're thinking, okay, this is the given part. So everything in black is given, okay? And after that, you have to use powers of analytical reasoning to move the problem forward. So now what we can see here is that we've got two smaller right triangles embedded here. And so if we look at the embedding of the smaller right triangles, we can just break up X into two quantities very simply. Now, when that's the case, ladies and gentlemen, you can make new labels. And the new labels basically say, okay, I'm going to call this particular distance this later and this distance this later, like we've done before, but you have complete flexibility. So just to make the problem simpler, I'm going to denote this distance here on this right triangle as A, and I'm going to denote this distance here as B. So now we see that X is A plus B. So if we can determine A and B, then we'll be done. So if you like, let's just call the first triangle 1, here the smaller right triangle, and let's call this triangle 2. So for 1, we have a 30, 60, 90. Now, of course, let's just go ahead and put in our 30 degrees here. And notice in this particular case, we have the longer side and we need the shorter side. Well, the shorter side is just the square root of 3 times the longer. So this implies that A is just the square root of 3. And I'll do the 100 first so it doesn't look so awkward. 100 times the square root of 3. This is just a 30, 60, 90. So that's previous result. Well, and of course I need to do it correctly. It's going to be smaller, right? Previous result. So we have to divide, right? Because it's going to be smaller. And let me be sure to focus this. Yeah, that looks a little bit better. So now this is what we're doing here. Notice the way I did this, we have S, and the reason I did this is because I need to check what I wrote here. Let's see, we've got square root 3 over 2, and then yes. So here, let me make this and do this. You all probably thought, Professor Ron. So notice here, when we look at this, we have L equals square root 3 times H over 2. So this is just square root 3 times S. And so if and only if S equals L divided by the square root of 3. So my formula here I need to fix. And it just occurred to me, that's why math is so wonderful. It tells you exactly what to do if you make an error. So this is L over square root 3. Makes a lot more sense. The thing like and this is good when Professor Ron makes a mistake in algebra, because again, this is what I want you to do. This is why I have you write out your work. When I write my own mathematics, do my own research, I'll go down the paper and I'll say, well, this isn't consistent with that. I must have messed up somewhere. And there we go, right there. So this is the formula. Of course, this is going to be smaller. The shorter side has to be smaller than the longer side, not bigger. So there you go. So now, in this case, we get A is 100 over the square root of 3. And now for 2, let's analyze this. Notice we have another 30, 60, 90. So we can go ahead and put in our 60 degrees up here. And in this particular case, we see that we have the shorter side here. And so now this is the longer side. So now we get B, get the square root. So B is 100 times the square root of 3. It's the longer side. Again, the previous result. There we go. So this is consistent. And consistency is what we like. What we're seeing here is now we're good to finish this problem. So by our construction, X equals A plus B. So this will give us 100 over the square root of 3 plus 100 times the square root of 3. Now, if we want to make this look beautiful, you know, and like I've said, when I do my videos and I do my lectures, I compute everything exactly. And if WebAssign wants exact, then you type exact. You could type this. If they want an approximation, you can use your Google calculator and they will tell you to do that. I'm still getting questions like, I'm not sure what to do. Well, if the problem does not request an approximation, you give an exact answer. If you need to use a square root, if you need to use a trig function like, sine of 2 radians, if you need to use pi, then use the little palette that will help you access the Greek letters and do an exact answer. And unless an approximation is directed for you, then you always do exact. That is the unwritten law, so to speak. So now let's just get a common denominator. That way it's easier for you to see. So we'll just do root 3. So of course this will be 100 now times 3. So we can make this look pretty, so to speak. So we can factor the 100 over root 3. I always like to do this because you did this in high school geometry, but I know it's been a while. So 100 over root 3 times 1 plus 3. So this just gives us 400 over root 3. And that's a nice, beautiful answer. And I don't care if the square root's in the denominator. That's a nice, neat answer. And of course, if you need an approximation, you can approximate it using your Google calculator. You all are very adept at using a calculator. Obviously, you use them too much. But when we have to do things that are a little bit more tricky, we'll also use them. For instance, in cases where we've got non-famous triangles, that is, we've got degree measure that aren't on the unit circle that we can't easily do, we'll have to do things exactly. And then if we use our Google calculator, I'll show you how to use the degree mode. For instance, the degree mode will do the automatic conversion for us so that we don't have to change the radian measure. It will interpret the degrees appropriately for us and then give us an answer that will be correct. So the degree mode actually does the conversion for us, and that's a luxury, but it's nice. It's nice because we like our degrees, and it's just one less thing to have to worry about. But if we do an exact answer, then we can move forward to any problem and say, here's the exact response. If you need an approximation, I can give it to you. I can give you a nice calculus approximation using Google. Okay, now let's look at another one.
Professor?
Yes.
Real quick before we move on, how did you get times 3?
Which one right here? You
Yeah.
all don't like the common denominators. Okay, if I've got a square root of 3 here, what's root 3 times root 3? See, when you get the common denominator, you have to multiply by root 3. What's root 3 times root 3, Simon? That'll be the square root of 3 squared, which is what?
3.
Yeah. Arithmetic, so is that okay?
Yes.
Okay. Ladies and gentlemen, when I do my lecturing, everything's exact. And so I'm glad Simon is asking these questions because this is very important. Again, remember, we always want to make sure that if we simplify things, that we have clean arithmetic. And if we've got clean arithmetic, if we slip up somewhere, we can fix it. Boom, we can fix it. If you're sitting there punching on a calculator or scribbling a bunch of chicken scratch or using a homework site to do fraudulent work, you'll never get anywhere. You'll never get anywhere. And that's why I teach the way I do. Everybody wants me to say, oh, well, Professor Ron, make it easy. No, ladies and gentlemen, easy is not going to get you a STEM degree. You get to the university and you won't pass. The idea, and I like it when Simon asks questions like this because these are at the heart of where you make most of your mistakes. Again, if you're stymied doing your WebAssign and this is, and it's 1 o'clock in the morning and that's the best you can do and you need an exact answer, that will work. But don't take out your calculator and approximate it when the question does not direct that. Then you get the big old X, and then you'll send me a WebAssign message saying, why is this wrong? I'm like, well, it didn't ask for an approximation, okay? So thank you, Simon. That was a good question. So let's look at another example. Here's one similar setup, and we want to solve for X. I promise I didn't mean to do it this way. Solve for X. And we'll use our nice triangles as long as we can. Then, of course, I'll do a problem that has terrible, terrible angles, and we'll be fine. Now, here's what's given, ladies and gentlemen. We have triangles within a triangle. So we have a large right triangle. Feels like we're in an English class with all the terms that we have to use. Triangle. So here we have the right angle, we have a 60-degree angle, and we have a 30-degree angle. And this leg here is 85. That's the given. Now let me notate where X is. So this is the similar kind of problem, just like the last one. So when you have examples like this, and I took this straight from the book at WebAssign. So this is stuff that you'll enjoy. So when we look at this, we're thinking, okay, we're going to do the same thing we did before. And if you like, ladies and gentlemen, we can just call this leg of this right triangle our favorite letter A. So we'll call this A. Well, you know what? Let me do this in another color because this is like additional. It's not what was given. So let me write this as in red. So we're thinking we might need to do a difference. So if we've got a right triangle here, and then we've got a bigger right triangle here, we're thinking we can now find this longer leg here of this larger right triangle and then do a subtraction. So if we can find the longer with the shorter, we can subtract to find X. Now, first, what we want to do is notate here. We've got a 30, 60, 90 here. So this is 30. So 30 degrees. And now, of course, this is a 30-degree angle. So this larger angle here is 60. So I'll just say this is 30, and this one all the way over here is 60. So we have two 30, 60, 90 triangles. So let's call the first triangle, we'll call it 1, and we'll call this 2. So now, again, let's just look here. Notice this is just like what we had before, so we get to repeat some of the logic that we did before. Notice here, for the smaller triangle, we have the longer side opposite the 6-degree, and A is the shorter. So A will just be 85 divided by the square root of 3, since these are easy triangles. 85 divided by the square root of 3. And again, that's the previous result. We don't have to use the trig functions with the sides of the triangle if we've got a simple triangle, and that makes your work more efficient. So put all of this stuff on a note card and have it ready to go, or just put it up here in the memory bank. So now we have A. Now let's look at 2. So we need to get this longer side here. Notice here we have 60. So this is the longer side of the larger right triangle, and here 85. Again, same deal here. 85 here is the shorter side. So this says that A plus X, I like this problem because it's tied directly into the last problem, will now be 85 root 3. So it's the same kind of problem, but it's set up a little bit differently. So what I want to do in this particular case is help you with these famous triangles so that you can use them to make your work more efficient. So now this implies, in this case, X, well, in this interesting, X equals X plus A minus A. And so we'll fill it in. X plus A is 85 times the square root of 3 minus, we'll do the same song and dance. I thought it was worth doing this. And now we can do the same thing we did before, get a common denominator. Okay, somebody help me out. What's root 3 times root 3? Anybody? What's root 3 times root 3?
3.
Excellent. Kong, you get 3 points. So 85 times 3, root 3, minus 85, root 3. So now we can factor. Looks very similar, doesn't it? So this gives us 85 over root 3, 3 minus 1. So that gives us a 2. And 2 times 85 is 170. So very simple problems using our famous triangles, but we're thinking, how could we have ever done this using our unit circle approach? We need the right triangles. So this is embedded in the trigonometry, but we don't really have to do the ratios directly because these are simple triangles. So I want you to see the difference there. Now, since that's just like the last one, this should embed this, and this should help you with your WebAssign. And then, of course, if you need an approximation, you can use your Google calculator. Now, we want to use some ratios. Let's see here. Yeah, here's a good one. Let's see. Yeah, let's try this one first. This is a nice word problem. Angles of elevation. So this is like a surveyor here, surveying problem. Example. The angle of elevation to the top of a mountain, to the top of a mountain is 32 degrees. 1,000 feet closer to the mountain the angle of elevation. So this is what a surveyor would do. The angle of elevation is 35 degrees. What is the height of the mountain? And you know what's interesting? That when we do our mathematics, we find it most satisfying when we write down enough detail so we can go back. So if you have enough detail there, you can always find a slip up. The detail's there, then you know what to do. So again, we remind ourselves of this every time we do any problem. Now, we can just go ahead and frame this in terms of triangles. So we've got the surveyor. So the thing is, here's our mountain right here. There's the height of the mountain. Here's our mountain. I mean, we're nothing fancy. And we have (32 degrees). We can just call the H the height of the mountain. And then if you move 1,000 feet closer, so here we'll mark this off. This will be 1,000. So this is why we did the last problems, because it's the same structure, but now we have terrible angles. We have a 35-degree angle of elevation. 35 degrees. So we're going to do this problem just like we did the previous two. That's exactly why I did them. So when we look at this, we've got two triangles, And we need to find H, but we're going to be hard pressed to find that if we can't use the triangles. Now, what do we tacitly assume? We tacitly assume that this is a right angle. Again, we're imposing right triangles as a surveyor onto the mountainscape. So whenever you use trig and you're dealing with triangles, you must have a right triangle. You must assume that, or you cannot just make it up. All right. So there's always, and then of course, as we get more flexible, we can look at triangles that aren't right triangles. We talk about areas of arbitrary triangles. We're going to talk about that soon. So now what we're going to do is we're going to call this distance X. And we can use both of the triangles. Notice we have the big triangle and the smaller one. So we're going to call the smaller triangle 1. And then, of course, the bigger one, which kind of covers all over, will be 2. That's the bigger one, which comes all through there, the right triangle. So it's not just this obtuse triangle here, it's the whole thing. So now when we look at this and we think about what we have, we can look at this in terms of just looking at both of the triangles. So let's look at triangle 1. So notice here, we've got this 35-degree angle, and we have the opposite side, and we have the adjacent side, okay? So since this is not a famous triangle, let's go ahead and use our trig ratios. So from 1, we have tangent of 35 degrees, which is not a very nice number, equals opposite over adjacent. So this is H over X. Now, when we look at this, we're going to get two expressions here. We can look at this and say, with each of the triangles, we can get expressions that involve X, or excuse me, H. And then we can set the expressions equal to solve for X, and then pick either of the equations to then ultimately solve for H. So this says that H equals, by cross multiplication, X times tangent of 35 degrees. Okay, so there's one equation that can be very useful to us. All right, so again, remember, opposite over adjacent. This is easy. This is general math, kids. Really, I'm sorry, this is general math. You probably learned this when you were in the 6th grade. So the thing about this is that what we're doing now is really much easier than what we did before, and you're probably doing a happy dance. So number 2, again, we want to look at the bigger right triangle. So now we can use the same functions. That is, we have this leg, which is X plus 1,000, as the adjacent side to 32, and then H as being the opposite. So we can use tangent again. So we'll say tangent of 32 degrees equals H over X plus 1,000. Now, equivalently, cross multiply, H equals, so we'll just say X plus 1,000 times the tangent of 32 degrees. Of course, we'll have to distribute that because that's what the algebra tells us we have to do. And so now, and this is a common occurrence with these types of problems when you have two triangles. Notice with the previous examples, we had two triangles and we got two results, and then we combined the results to find the actual value of X. So we're doing exactly the same thing here. What we're noticing is that we'll just have to do a little bit more work. And now what we can see is that these two equations define H algebraically. So we can set these equations equal to solve for X. So by combine 1 and 2. It's like when I'm doing calculus, I say converge, so they know that the series converges, and we say combine. I will articulate certain syllables of words just to emphasize what you need to do. That's just something that I do, and it is somewhat silly, but it's my way of just say, please note what I'm doing. So now, notice here, we have X plus 1,000 times tangent of 32 degrees. We'll multiply all this out. It's like doing logarithms, equals x times tangent of 35 degrees. So now let's distribute. So we have x times tangent of 32 degrees plus 1000 times tangent of 32 degrees. And of course here, this is multiplied. So I guess I'll put that a little bit closer. And this equals x times tangent of 35 degrees. Now, what we want, excuse me, what we want to do is get all of our x's on one side. Now, here's something that I've noticed. Here's something that I've noticed. If we leave this here and take this over, we don't have as many negative signs. So let's just take this over because it has an x and leave the non-x on the left-hand side. So 1000 tangent of 32 degrees. So we're going to have x. So we'll have tangent of 35 degrees minus the tangent of 32 degrees after we factor right there. So take this over, extract the x, and we have the tangent 35 minus the tangent 32. And now, of course, we can divide. So equivalently, x equals 1000 times tangent of 32 degrees divided by tangent 35 degrees minus tangent 32 degrees. So this gives us what we need. Now the interesting thing about this particular problem is this. We've done the hard part. So now we just go back up here and say, well, which will be easiest to use? Well, clearly this one, because if we just multiply x by tangent of 35 degrees, we get h. So we're going to be lazy. And so then by 1, h equals x times tangent of 35 degrees. So that means we just multiply the expression for x by tangent of 35. So just tack on another tangent upstairs. So this says 1000 tangent 32 degrees times tangent 35 degrees divided by tangent 35 degrees minus tangent 32 degrees. So there is your exact value right there. And everybody asks me all the time, well, you want us to do our problems a certain way? No, I don't. I want you to do them the correct way. And that's correct. There's nothing convoluted about how I do my mathematics. I do it correctly. I do it the way you should do it. And if you want me to be able to follow your mathematics, you've got to write it clearly. Notice I don't have a single approximation here, as you shouldn't have any. When you do these problems, you do them exactly as I have taught you. Now, at this point, you can use your Google calculator to get a nice approximation if the problem requests it. Okay, so if you're taking a test, I might say, find an expression for the height of the mountain, and this would be the answer. Or I would say, compute the height of the mountain to 1 decimal, something like that. So then you get this. I would look at your work and I expect to see this, and then the approximation. This is just like doing any problems. What I don't like is when you clearly disregard everything I've said and you put a bunch of decimals in everything, which is hideous. Why is it hideous? Because you have introduced round off error unnecessarily. I never teach that way. You see, if any problem I do, at the very end, I'll either do an estimate or a Google approximation, just like in the Smart Pen videos. That's what I always do. The problem is exact to the bitter end. And the idea is even if, and some students are actually good, they'll do their decimals and they'll run them out so far that you can't have any worry about round off error, but that's so tedious to write all that stuff down, and you could make so many mistakes in doing it. So if you follow this technique, you'll always have a nice clean answer. Now, what I want to do, let me find my let me move this down and find my Google calculator. Okay, so we'll go to Google. Let's see here. There we go. So let's go to Google and approximate this. I love Zoom. This is so nice. Okay, so here we've got, let's do parentheses or parenthesis 1000. Now notice we need degrees. So go ahead and click degrees. So it'll do the conversion for us. So degrees. So we'll do 1000 times tangent 32 degrees. So it will do the conversion for the tangent degrees for us times tangent of 35 and close that out. Then divide by the denominator, use your parentheses, tangent 35 degrees minus tangent 32 degrees. This is the only approximation you have to do. And this gives us 5,807.655. 5,807.655. And this is in feet. So the interesting thing is here is that when we do this, okay, yeah, same old questions about algebra. You all really, you tickle me with your algebra questions, and that's good because that means you're thinking. So now, say we were doing this as a WebAssign problem, and the WebAssign asked for a particular approximation. Maybe it wanted to the nearest first decimal or nearest integer or whatever. You just follow those directions. So work the problem out exactly using your ratios. So now we're thinking, wow, we could have started with triangles, right? We could have started with triangles, but all that stuff that we learned about the trig functions, which now we can just rely on, we'd have to kind of reinvent. So we've got our graphs, we've got our inverse trig functions, we've got our algebraic expressions, we've got our values, we got everything under the sun about trig. And now we've added the extra interpretation with the right triangles, which again makes us feel very powerful. So now you can do your engineering problems, you can do your physics problems and enjoy the right triangle approach. Now, what I want to do is say a little bit about, and you should master this problem. You should master this problem and all the other problems that are similar to done just like this. You just dissect it, you use the algebra, master this, practice it, teach it to someone, teach it to the wall.
Professor,
Yes.
so why is it that you use tan?
Use tangent
Yes.
because it was easy, opposite over adjacent. See, opposite over adjacent, opposite over adjacent.
Okay.
So Jay, that's a good question. Let me go back to the very beginning. See here, tan, opposite, adjacent.
Oh, okay. Just fall. Okay. Now I see.
Yeah. Jay, that's a great question. Now listen, everybody. Jay had a wonderful comment here. Notice, when we use the famous triangles, we don't have to worry about this. But now his question is, why do we use tangent? Notice we have the opposite over adjacent from our definition of sine and cosine. And so when we go back to the problem here, we see that 35 degrees, we have opposite over adjacent. That is the opposite side of 35 is H, the adjacent is X. So we get that. And then we did the same for 32 right here. Okay. So again, you can write in opposite over adjacent. So now, and here's a really good point. All of these little ratios, put them on a note card. Now, of course, if you know sine and cosine, you know the rest, but this was the first derivation I did to move the functions into the realm of the right triangles. Okay. And all the sign conventions are the same, ladies and gentlemen. The pluses and minuses, it's all the same. You know, it's like Professor Ron is like a broken record. You all are going to be able to do exactly what you need to do. Now with the right triangles, you can do some fun problems. So excellent question and observation, Jay. Thank you. So now what about triangle area? Someone help me out. How did you compute the area of a triangle in geometry? What, anybody help me out? How'd you do it? Did you have a formula? Anybody? Don't let me call on somebody. I don't want to embarrass anybody. Kung, what's the formula for area of a triangle? Anybody?
Wasn't it 1/3 base times height and
Well, almost one half
one
what?
half, 1/2? Yeah, sorry. Yeah, 1/2.
Yeah, one half base times height. Let's see if somebody in the chat room got it, Jay. Oh, yeah. Jeremy Alexander Sorrelzano. Very good, Jeremy. You get 10 points. And Jay, you get 10 points. And Kong, you get 10 points for participating. Okay, so let's use it to solve for a new formula. So as all of you smart people said, we have area of a triangle is 1/2 base times height. Okay, so let's use that to get a generic form for area using trig functions. So here's our theorem. Okay, now what we're going to do is we'll say, consider a triangle, and not a specific triangle, just a triangle with sides A and B with included angle theta. Now, I'm sorry about the thetas. We just love theta. We'll use alpha and beta and phi and all of those. And you know, it's, and with my Southern accent, sometimes you're like, what is he saying? So forgive me for that, but that's just part of it. I always tell my students that it's faded over the years and they don't believe it. And I don't think I do either. So what we want to do, what's the result here? Then area of the triangle is, and it's going to be reminiscent of this, it will be 1/2 AB sine theta. So you're thinking this formulation is more user-friendly, because if you have the base times height, you clearly have to be able to compute the height of the triangle. And maybe it's not a nice triangle. Maybe it's not a right triangle, and then it would have to be given to you. So with this formulation, it's more user-friendly. So let's say, why is this true? This is easy. You'll love this. Why is this true? Not like the proofs I did last week with the inverse sine is odd, and then the other one that, you know, the complementary angles. Well, you know, that was a good proof, and I hope you've studied it, because if you've studied those proofs, you understand the inverse trig functions. So now here's case one. Let's just consider an acute triangle. So we'll do something like this, just very simple. I'll draw this in pencil. Okay, so we have an acute triangle. Okay, now we're gonna take the hypotheses that we have here. We're gonna have a side A and a side B, and included angle theta. Okay, so now this is, I'm glad Jay mentioned what he did, because we're going to use those ratios now, because we don't know what theta is. It's just an acute angle and could be anything. So here's what we're going to do. We're going to drop the perpendicular. So by constructions that you did, you know, in your geometry class, that was always fun to do geometric constructions. We're going to call this perpendicular that we've dropped to the opposite side of this angle, H, the height. So by definition, this is the height of the triangle. Now notice, what do we have in this problem that's user-friendly? Notice relative to theta, we have the height and we have the hypotenuse. I know that's a bad choice because that reminds you of hypotenuse, but it means height. So we can say opposite over hypotenuse. Notice one more time, relative to theta, opposite, hypotenuse. So we say this implies sine theta equals opposite over hypotenuse. What's the opposite? Well, it's h. What's the hypotenuse? B. If and only if h is equal to b sine theta. Right there. So in order to finish, we just have to use this and we're done. Now, of course, the base is A, so we can just note observe. And of course, we use the letter to denote the actual side and the length. Again, we're lazy. Observe, the base is A. So this implies area equals 1/2 base times height. And so, of course, we just fill it in 1/2 A and then B sine theta. Now that's for the first case, for the acute triangle. So again, this is a much more usable formula. And of course, you can write it down exactly. And if you're a surveyor or you're in a physics class and you need a nice Google approximation, you don't even have to convert. For instance, ladies and gentlemen, if we went ahead and did the conversion, we could stay in radian mode. So that would mean we would need to have the pi over 180 to convert from the degrees to the radians. But you know, it's okay. It's okay to use that mode on your calculator. We know what it's doing for us, and it's very helpful, especially when we need a nice approximation. But always remember what you're doing, just like when we're doing sector, area, or we're doing arc length, where we have to use radian measures. So we always do that conversion as we did last class. Now the case 2, now you're thinking when we do these types of problems, usually we'll just have to exhaust the reference triangle in doing a lot of calculations. But here we know that the types of triangles in Euclid's geometry, they come in this form and they also come in the obtuse form. So let's write that, let's just draw one of those just to help us with our logic. Pictures are helpful for logic. They don't give us the proof, but they certainly help us to organize our work. So now we'll do this. So here's an obtuse triangle. Again, we'll do the same thing. We're going to call this side A, this side B, and the included angle theta. Now, in order to make this work, we're going to extend the base here. Do an extension of the base and drop the perpendicular. Okay, so we're going to drop the perpendicular here. Now notice, and this is what I like about this, because this is what we're using from chapter 5. Theta is in the second quadrant. So this angle here is just the reference angle, theta hat. Because if theta is in the second quadrant, then the reference angle or the reference number is pi minus theta, which is exactly what that is right there, because these are supplementary. So that's the reference angle right there. But again, it's going to have the same value as this, because in the first and second quadrant, the sign is positive. So again, reference to what we've already done. So now when we look at this, this is easy to actually construct. Now we're thinking this red thing here that I've dropped, that is the actual height. And so we're going to use the same construction. I'll do this in red since I'm doing all this in red. So we look at this and say, oh, and let me put the B, ladies and gentlemen, closer to the actual side so you can see here's the B right there. It's this guy right here. So that where I had it, it looked like it was labeling the other. So now we can see we'll use the same trig function relative to theta hat. We have what? Opposite over hypotenuse. So sine of theta hat, which is also, since theta is in the second quadrant, this is sine of theta. So we're using our work from chapter 5, and I don't need a hat anymore because these are equal. This equals opposite over hypotenuse, H over B. So we've got the same construction as we have here. So I'll go ahead and write this in, opposite hypotenuse. So now equivalently, H equals B sine theta. So now it's the same thing. So we're done. So we just had to show that we could still get the height in this form. So this implies, just like in the first case, that area equals 1/2 base times height, which is now 1/2 AB sine theta. So now we're thinking well, look at it this way. This is a much more user-friendly formula, isn't it? Because now when you're doing a physics problem or an engineering problem, if you take my colleague Nate Wiggins, if you take his engineering classes, this will come in very handy. So this is a more user-friendly formula that utilizes trigonometry, but just remember the hypotheses. You have two sides of the triangle with the included angle, two sides of the triangle with the included angle, okay? And that will allow you to compute the area of the triangle. So much more user-friendly, albeit very simple, very, very simple. But again, we see that we can get at this formula using the right triangle approach to trigonometry, okay? And you know why I like the right triangle approach? Because it is self-correcting. It is so much more self-correcting because as you work with things, with these ratios, things have to align. And if things start to go off a little bit, you can always tell. Whereas when we were working with the unit circle, you had to be very vigilant because you didn't have as many checks. Here the checks are embedded, and then we get to use all of our ideas about reference angles or reference numbers because now they're turning out to be exactly the same. So that's one less thing we have to worry about. Okay, good. Now, what I want to do is just a simple calculation that pulls together the sector area with the triangle area so we can get a little practice with it. And then I want to talk about some algebraic expressions with inverse trig functions. Now, as you work through these examples, you're going to see that you're asked to do the same kind of calculations you did in chapter 5. There'll be absolutely no difference. And so you're going to get a big break there. Now, let's use this newfound formula. So we've got a circle. So let's see if we can do a freehand circle. There we go. That's not bad, kind of Charlie Brown, but that's all right. So now here's what we have. Let's kind of eyeball the center. So we've got a circle of radius 2. We have circle of radius 2, and we have central angle 120 degrees. And then we have a lune. So draw the chord. And we're going to shade the lune. It's like a calculus problem, but not quite. When you do polar coordinates in Cal 2, you'll do more work with this. So compute the area of the shaded region. So now when we think about this, we're like, okay, this is not a difficult problem, because if we look at all of this, that's just the sector area. And of course, if we subtract the triangle area from the sector area, we get the shaded region. So we'll say area equals sector area minus triangle area. So the larger structure is the sector. One of the smaller structures is the triangle. And then of course, the region here is what we call the lune. Okay, so now we're thinking, well, let's just go ahead and write down what this is. This is 1/2 r squared theta minus 1/2. We'll just use the notation from our theorems, AB sine theta. Now, of course, simple, right? We know what theta is, and we're going to have to convert it to radians, so we'll do that. But let's just go ahead and fill in the r for the circle, again, is 2. And then, of course, the 2 legs are also 2, and the included angle. So we've got a lot of overlap here. So this will be 1/2 2 squared. Theta will be what? 120 degrees times, this is what I said before, 180 degrees downstairs and pi up here. That's the conversion factor, right? So we're not using our calculator, so we have to do it. Then minus 1/2, and of course, A and B are both 2, so we get another 2 squared. And then we have sine of what? 120 degrees. Again, 120 degrees is 2 pi over 3. So either way you want to look at it, it's still the same calculation. So we don't have to convert that. Now notice we have these common factors here that we can extract. So we have basically 1/2 times 2 squared. And now, of course, we can divide by 60 here, so we just get 2 pi over 3. Minus, and now, of course, the reference angle here is just 60 degrees. That makes it easier. Sine of 60 degrees. So that's just pi over 3 radians. So now, of course, we have 1/2 times 4. So we get 2 pi over 3. And of course, sine of 60 degrees is sine of pi over 3 radians, which is √3 over 2. So of course, 4 divided by 2 is 2. So we get 2 pi over 3. And then multiplying by 2, we get 4 pi over 3. And of course, here the 2's absorb, minus √3. So when you look at this particular problem, very similar in how we construct the idea when we did the solve for x with the triangles within triangles. When we had the nice angles, well, this is a similar problem. We have a very nice angle here. It's a very complementary angle. I mean, that complement with an I, not the complementary type for the right triangles. So when we look at this, we're thinking this is like doing the 30, 60, 90 triangle. We've got nice angles, and so we can do a nice exact calculation, unlike the one where we had the surveyor and we had the tangent of 32 degrees and we had the tangent of 35 degrees. We still can write an exact answer, but then if we need an approximation, we can do that. The nice thing is, even with the exact, without the trig functions, we can still do an approximation of it. So they're still the same. In both cases, the answer, the response is exact, and we prefer that. So again, what I want you to see here, what is mathematics? I mean, last night I did a derivation here about Pythagorean triples, And I thought it was kind of interesting because when you do mathematics, what is the idea behind mathematics? It's like, oh, it says, where did sine of 60 degrees come from? Okay, well, that's not difficult. What's the reference angle for 120? Be 180 minus 120, which is 60. Okay, that's the reference angle. So if theta equals 120, you all should know this. Theta hat is just 60 degrees, and they're equal because they're in the first and second quadrant. Okay. I didn't see that. Oh, that's fine. That's good. So remember, everybody, you can, excuse me, doing my Peloton early in the morning, sometimes it's a little bit cool where I live, and I get a little bit raspy, but that's fine. That's what Professor Ron loves to do. I love to run and love my Peloton bike. But the thing is that remember, like I said before, on the unit circles, you've got degree measures and you've got radian measures. And I always say, well, you can use the unit circle directly, or you can just always use the reference number or reference angle. It's your choice. I usually like to use the reference because I can move everything back to the first quadrant. It's easy to keep track of signs in the quadrants. You don't forget that. But we do so much with reference angle, reference number, that it's sometimes simpler to look at it that way. But you have whatever choice in the matter. You can compute it any way you like. As long as it is a correct calculation, you're fine. It doesn't matter at all. Okay, now let's look at a couple of things that have to do with inverse trig functions, and also we're going to have to start thinking about solving basic equations even before we get to the ultimate part of this course, which is solving equations in general. So it's going to be like college algebra again. So with this right triangle approach, we can look at inverse trig functions, at least compositions, in a way that will be simple to us. Because, like I said before at the beginning of the lecture, we could have already done this with the Pythagorean identities. But what I like is to actually do this when we have the use of the right triangles. So in 6.4, we revisit the inverse trig functions. So last night I was doing a little derivation here with the Pythagorean triples. And let's see here, where did I did like a summary of this. Let's see, so we've got this, and then let's see, C over B. I actually did a summary of this somewhere. Oh, here we go. Here we go. So I started scribbling here, and then I came up with some formulas, and then I checked Wikipedia, and it was exactly right. I've got a couple of number theory books at the college that are in storage, and so I had to derive this on my own, which is fine. It's what I normally do anyway. But I love my number theory books. They're wonderful to have around. So, for instance, we could say like m greater than n, where m and n are natural numbers with different parity. That is, one's odd and one's even, or vice versa. They're not both odd, they're not both even. And then for the Pythagorean triples, I got these nice formulas. M squared, well, this is where I finished the calculation here. And then I checked a nice example of it. So we have A equals m squared minus n squared B equals 2mn, and then C equals m squared plus n squared. And it's kind of interesting, Wikipedia used the same letters because when you do a squared plus b squared equals c squared, the Pythagorean equation, you need integers, and you want to solve this in the integers. So you want to be able to actually construct the infinitely many Pythagorean triples that exist. And so I thought, well, wouldn't this be an interesting thing to look at? So now when we think about this, you know, we can look at this and say, okay, well, let's start with the simplest one. Let's say we have the following. So we're going to say let m equal 3 and n equal 2. Okay, so m is 3, n is 2, 3 is bigger than 2, so we've satisfied the hypothesis, and they have different parity. This is odd and this is even. So this implies a equals 3 squared minus 2 squared. So that's 9 minus 4, which is 5. And then we have b equals 2 times 3 times 2. So that's 2 times 6, which is 12. And c will just be 3 squared plus 2 squared. And this will give us 9 plus 4, which is 13. And there's a nice Pythagorean triple. This is a fascinating result. When I was an undergraduate taking Dr. What's that dude's name? He's no longer with us. Dr. Fred Wright, Dr. Fred B. Wright. He had the big old glasses, and just a brilliant man. I knew his daughter who took a lot of French classes with me, and she was so much better at French. I said it's amazing. She says, but you're a good math student. I said, I know, but you know, she would help me with my French because she was very good. But the thing is that Dr. Wright was a great professor. And he just loved talking about the Pythagorean theorem and the Pythagorean triples. And so now that reminds me of this. So he would say, now you have infinitely many Pythagorean triples. So now when you look at this, you can say we can draw a triangle. So it, again, something like this. So here's our hypotenuse, 13. We have a leg of 12 and a leg of 5. That's a Pythagorean triple right there. 12 squared plus 5 squared equals 13 squared. That is 144 plus 25 equals 169. So you can generate as many as you like. And so you're thinking, all right, so how do the inverse trig functions work? How does this work? Okay, well, now we can use inverse trig to get expressions for the angles here. So if you like, we can call this angle theta. Now this angle here will just be a supplement of this. So if you want, you can just call this alpha, okay? Well, of course, that's 90 degrees, so we're done this. So if we wanted to like solve the triangle, then we could say, all right, well, we can just basically figure out what the angles are using the trigonometric relationships. Okay, so let's look at it this way. Say, for instance, we want to go ahead and, you know, we've got complete rain here. So let's just say for theta. Now you get your choice. Let's just be fun here. So notice here we have theta. We'll use cosine. We have theta is what? Adjacent over hypotenuse. Cosine theta adjacent over hypotenuse. So we can say cosine theta equals adjacent. Write it out. So now remember, and I keep going back to this, so I'm glad Jay made the reference to tangent. Let me find it. I think I've stuck it in the, here we go. Going back to these, cosine adjacent over hypotenuse. So put these on note cards. So now we're seeing where these right triangles are very useful. So this will be 5 divided by 13, okay? Now, when we define the inverse trig functions, we actually started with the inverse trig function. Now we're going to apply it. Now we're going to apply it. So we're going to say if and only if theta equals the inverse cosine of 5 over 13. Right there. Right there. That's it. That's the angle right there. Exactly. Now, if we're doing a problem in physics, maybe your professor says, okay, you know, you don't have an infinite series here, so you can use your calculus approximator and give me an approximate angle in degrees. Or he might say, well, no, I need it in radians. So you'd have to make sure you were in your radian mode. But this as it exists right here, this is radian mode right here. These are radians because these are pure numbers here, pure numbers. And then of course, alpha, this implies alpha is just the complement of theta because we know alpha plus theta is pi over 2 radians. So this would be pi over 2 minus inverse cosine of 5 over 13, right there, all in radians. And so now you can see how we can use the inverse trig functions to run the cosine equation backwards and actually find the angles. You see? So when we do the 30, 60, 90 triangle, we don't have to worry about it. We already know it's a 30-degree angle. We already know it's 60. So those are the more convenient ones. But think about it. If you've got the sides here of the right triangle, then it's just simply choosing your favorite inverse trig function. We like to maybe pick the ones that we use the most, you know, inverse cosine, inverse sine, inverse tangent. You could use the other ones, but these are very user-friendly and they get, you know, they're straightforward, and we'll use our Google calculator. We see them the most. So we just keep it kind of simple. So the idea here is, like I said, now we have this. Exactly. And you can do with them as you need. If you need approximations, you have exact, these are exact, then you do one level of approximation and you're done. Okay. You do not do an arithmetic calculation with round off with decimals and then round it again and round. No. You start with exact and boom, you get the approximation, one level of approximation. That way there's no round off error. Okay, you don't approximate this and then subtract from this and do another approximation and ruin your calculations. You do it like Professor Ron does. Okay, and there should be no question about this because this is how I do all of my work. It will not change. Now, if that's the case, and I just made this problem up, but it actually is working to my advantage. So now we can say the following: compute the following. That is, with what we've done here, I want to show you that it's actually very helpful. We want the secant of the inverse sine of 12 over 13. Now you notice why when I computed this and why I'm doing this, because this is the same right triangle. Now you can actually compute this, and then if this is an x, I'm going to show you at the next class how to do the algebraic expression. Now before, you're thinking, well, we could have done this before, Professor Ron, but now we have the luxury of the right triangle. So we want the secant of the inverse sine of 12 over 13. Well, we do just like we did up here. Okay, let's just say we're going to make an assignment. So keep the eye on this. This, we're going to make an assignment. We're going to let this be theta for obvious reasons. So theta, I'm just going to take this calculation backwards, will be inverse sine of 12 over 13. But what does that mean? apply sine to both sides and use the inverse equations to absorb that. So sine theta equals 12 over 13. Oh, sine of theta 12 over, oh, it's that triangle right there. That's the triangle right there. So when I do this, I can construct this. So if I didn't have this already, I'd say, oh, that's opposite over hypotenuse. Theta opposite over hypotenuse. Boom. And then Pythagorean theorem. Then I'll say 13 squared minus 12 squared. I could do, you know, let's be fun about this. This will be what? So 13 minus 12 times 13 plus 12. Just do the difference of two squares just to be fun. That's 1 times 25, right? So this implies the leg here is 5. So this is a 5. So just using the Pythagorean theorem. So now it's exactly that, isn't it? So you can see why we waited to do this. Now we're thinking, okay, this is just secant of theta. This is just secant of theta. I've got the triangle. Secant of theta is what? Hypotenuse over adjacent. Hypotenuse over adjacent. And that'll be 13 over 5. Which is what we kind of saw here. So the key here, and don't always think you're going to get a nice Pythagorean triple here. Sometimes it could be ugly and not have a bunch of radicals in it and stuff. That's okay. Doesn't change anything. But notice with the use of the right triangles, we can see how user-friendly the connection is with the inverse trig functions, but we're always having to think reference triangle, because with inverse cosine, we can go from 0 to pi. And then of course, with the inverse sine, we go from negative pi over 2 to pi over 2. So it's a little bit different. So we're always focusing on the reference triangle and then attaching the appropriate sign as we've done before. But notice here that all of this checks out. Once we draw the triangle, then we can just say, okay, well, this is just secant of theta. Well, secant of theta is hypotenuse over adjacent. And let me, here we go. So secant, hypotenuse adjacent. Okay, just like we did at the very beginning of class. So this is kind of the roadmap to what we've been doing today, isn't it? It's amazing, isn't it? And it's simple. So when you get to calculus and you're doing all these inverse trig integrals and you got all this, you're going to think, oh, thank you, Professor Ron. Now I can do this. This is easy. So the beauty of this is that we can now use the luxury of the right triangle to do these compositions very easily. So just one more and we'll be done. And then we'll finish up with this and then talk about the law of sines. So let's try one more and we'll be done with this. Example. What if we wanted to compute tangent of inverse sine of 6 over 7? You can make these up. They just have to make sense. So now, of course, this is our theta. So theta equals inverse sine of 6 over 7. And of course, by definition, this means sine of theta equals 6 over 7. Okay, so now we can draw our right triangle, our reference triangle, theta, opposite over hypotenuse. Remember, this is opposite over hypotenuse. So 6 over 7. And then this side here, we'll say 7 squared minus 6 squared. I'll just go ahead and write it out. I mean, it doesn't matter. We'll just do, so this will be, I don't know, let's do it. 7 minus 6 times 7 plus 6, and that's 13, right? So this is not a pretty number. So we get, this implies that the shorter leg here is square root of 13. So now when we do this, we get 36 plus 13, that is 49, and the square root is 7. So we don't get beautiful numbers here, but that's okay. That's all right. You know, it doesn't matter. I'm always just factoring the difference of squares just to remind you that you know that formula. And so now this equals tangent of theta, which is opposite over adjacent. So we do opposite over adjacent. So this is 6 over root 13. So now you see how simple this is if when we're working with inverse trig functions and these kinds of compositions where the inner function is inverse trig. Because once you make that assignment, you create a right triangle, a reference triangle, which then you can solve. You can look at the outer function and do tangent of theta. Now, of course, you don't have to call this theta. You can call it alpha, anything you like, you see? But the inverse trig functions mesh very well with the right triangle approach. So we could have done this with with the Pythagorean identities, but it would have been a little more difficult. Whereas it's nice to wait to this so you can just kind of have that easy luxury of ratios of sides of right triangles. So as I've said a million times, this note card. Now, once you use these several times, ladies and gentlemen, this will be common occurrence to you, just like the unit circle. But right now, this is something you really need to embed up here. When you think sine, opposite over hypotenuse, cosine, adjacent over hypotenuse. And then our best friend, tangent, opposite over adjacent. And then the others, you just take reciprocals. So what we're going to do next class is we're going to continue with some more topics with the inverse trig, finding the angles and doing some algebraic expressions, then talk about the law of sines, which is going to be a way to treat generic triangles, which not a big favorite of Professor Ron's. I mean, it's a good topic, but it just gives you a little bit more experience working with triangles. And you know, when you're taking your physics and you're taking your engineering, it's great to work with triangles. It's just that I know how many difficult things we have left to do, and I just do it because it's part of the student learning outcomes, but you'll like it. So I appreciate your attendance today. I hope you've enjoyed the introduction to the right triangles and see basically how easy it is. And now you can go back to chapter 5 and think about things in two different ways. It's like, oh, now I have the luxury of the unit circle. I have the luxury of the right triangles. And you can see why we use the unit circle for those topics, and then how they transfer very neatly in many cases to the right triangles. So have a great day. Enjoy the warm, balmy weather. And if I don't see you at the conference hours, I'll see you next class Thursday. Everybody have a good day.